In this section, we'll be looking at the inverse and properties of our z-transform. For our first inversion method, the partial fraction method, we can express our transform as partial fractions, then by inspection, recover our original signal. It's similar to how we perform the inverse Laplace, except with the z-transform, we have to be carefully considerate of each term's poles and its relationship to the region of convergence. And so if we look term by term and we compare the pole to the region of convergence and find that our pole is within our region of convergence, so z is greater than our pole, then that term is said to be a causal term and we don't have to invert or make any changes. However, if we have a pole that is outside of our region of convergence, so z is less than our pole, then that term is said to be a non-causal term and we actually have to invert it. And so just to quickly illustrate that, if we have some single term in x of z, where x of z has its own region of convergence, when we perform the inverse by inspection, we find that it's ak times dk to the power of n times a unit step. And when we compare the pole to the region of convergence of our x of z, if we find that it's within our region of convergence, so z is greater than our dk, then this term is said to be a causal term and we don't have to invert it. However, for another term, if we look at the pole and find that dk is greater than our z, so it's outside of our region of convergence, then this term is said to be a non-causal term and we actually have to invert it. And so we put in the negative and we flip and shift the unit step or any associated functions. For our long division method, if our x of z is a rational function, we can perform polynomial long division and instead express it as a geometric series of powers, and thereby the inspection and inversion back to the time domain is much easier. And so just a quick example, if we have some rational function x of z with its region of convergence defined, just to know what that region of convergence, it is said to be a causal signal because of it, meaning that in the time domain it exists for k greater than or equal to 0, or it's a right-sided signal. And so when we perform the long division, we get expressions as simplified sequences of powers, and then by inspection we can say that it is shifted impulses, where the coefficients are actually the amplitude of our signal in the time domain. It's important to note with the long division method that we don't actually get a analytical solution to our problem. Unlike the partial fraction method where we can actually get an expression in the time domain, here we're obtaining our signal one sample at a time. And so each time we perform the long division, we get one sample. And so with this example, we performed the long division 4 times and we were able to get 4 samples. Manually, this method would be extremely tedious if you needed more than just a few samples, but over the partial fraction method, this is much more suitable for computers. However, if we wanted an actual expression, then it's better to use the partial fraction method. For our last method, the inversion integral method, our inverse is given by this integral, where we're integrating along a closed loop, or an enclosed contour in our z-domain, where we choose the bounds such that it encloses our region of convergence and all the poles of our z-transform. However, this integral becomes really difficult to solve when our x of z is a rational function, which is more times than not, and so this method kind of becomes impractical compared to something like the partial fraction method. And how do we simplify it to actually use this method? We can take advantage of Cauchy's residue theorem to indirectly solve the integral. And his theorem states that we can sum up the residues of our z-transform multiplied by z to the n minus 1, and that will be the same as solving this integral. Our residues are defined as the evaluation of our z-transform at the poles within our contour. And so if we evaluate our z-transform at the poles of our contour and we sum up each of those terms, it is the same as solving this complex integral.
Alright, properties of z-transforms. Linearity, so for any two signals with the respective transforms and any two constants, it can be shown the following relationship holds. which is just two signals multiplied by two constants respectively, give two z transforms multiplied by those two same constants as well. And the proof for that is described here. And it's just pretty much self-explanatory. It just splits up the summation over here and goes along until we get what we have over here. This can be changed into this. Time shifting. So for any given transform pair, the following is also valid, which is just for any signal x can be time shifted by some constant k. We get the z transform multiplied by z to the power minus k. And the proof is here below. We just define a new variable here in the definition for the z transform, new variable n, which is equal to n minus k, which we replace here. And then as we go along, we take z to the power minus k out, which we then multiply to our definition of the z transform here. Time reversal. So for the given transform pair, this is also valid, which is just so for some time reverse signal, we get its z transform, which instead of z, we have z to the power minus 1. The proof is also here, and we define a new variable, m is equal to minus n, and we also see that in the equation, the summation begins at m is equal to plus infinity, moving towards m is equal to negative infinity, adding terms from right to left. This doesn't affect the result. It doesn't matter whether we add terms from right to left or the other way around. And yeah. Then multiplication by an exponential signal. So for the given transform pair, the following is also valid, which is just some signal multiplied by some constant to the power n, which gives us the z transform, which is time scaled by 1 over a. And we have the proof over here, and we can just give a and z the same power, which is minus n. This is the definition of z transform. Just replace z with z over a.
Our convolution property holds the same as our other transforms, where if there's a convolution of our two signals in the time domain, it's the same as multiplying their z transforms in the z domain. And we use the convolution and z transform definitions to come to that conclusion in our proof. And so z transform, like our other transforms, is useful in avoiding convolution, where we can just simply take the z transform and do our analysis there and invert back to avoid convolution. Our differentiation in the z domain states that if we're to take the derivative of our z transform in the z domain, it's the same as multiplying by n to the power of k of our time domain signal, where k is representative of our order of differentiation. And we can prove that by actually taking the derivative and coming to that conclusion. Our initial value theory states that for causal signals only, this holds valid, and we can find the initial value of our signal if we take the limit as z approaches infinity of our z transform. And through the proof, when we express our z transform as a geometric series of powers and take the limit as z approaches infinity, every other term approaches 0 except for our actual initial value. Our correlation property states that if we're trying to find the correlation or similarity between two signals, it's the same as multiplying their z transforms, with one being in respect to z to the negative 1. And when we take the definition of correlation and the z transform and work through that, we can prove that to be true. And our summation property states that if we have a summation of our time domain signal in time, it's the same as multiplying the z transform by z over z minus 1. And to prove that, we use the linearity and time shifting properties. And our summary shows the notable properties as well as a table of signals and their respective z transform that we'll be using in the worksheet.